In this epoch, the cosmos was a glowing fog, a dense, hot soup of protons, electrons, and photons, all scattering off one another in a chaotic dance that rendered the universe opaque. A wall of fire stretching in all directions, yet beneath this luminous fog, the dark matter was already at work, silently laying the foundations for everything that was to come, while the ordinary matter, the baryons, was coupled to the radiation, pushed and pulled by the intense pressure of photons, acting like a fluid that sloshed and oscillated in sound waves we call baryon acoustic oscillations. The dark matter remained aloof, indifferent to the radiation, interacting only with gravity. It was the anchor in the storm, the seed of stability. As the universe expanded and cooled, the ordinary matter eventually released its hold on the light, a moment known as recombination, and the universe suddenly became transparent, releasing the oldest light in the cosmos, the cosmic microwave background. If we look closely at this ancient light today, captured by instruments like the Planck Space Telescope, we see a modeled map of faint temperature fluctuations, tiny ripples in the fabric of the early universe. These ripples are not random static. They are the fingerprints of dark matter, the echoes of the gravitational wells that had already begun to form in the deep past, marking the places where the density was slightly higher, where the dark matter had begun to pool, creating the initial blueprint for the cosmic web. From these subtle seeds, the great drift began as the universe stretched outward, fighting the pull of gravity. These overdense regions of dark matter acted as gravitational attractors, slowing the expansion in their local vicinity and eventually reversing it, causing the matter to collapse inward. This process, known as hierarchical clustering, is the primary engine of cosmic construction, a bottom-up method of building a universe where small halos of dark matter form first, collapsing under their own weight, and then slowly merge to form larger and larger structures. It is a process of unhurried violence, a silent accumulation that takes billions of years. Imagine a vast, three-dimensional tapestry of invisible threads, woven from the fabric of space itself. In the early universe, these threads were thin and tenuous. But as the eons passed, the dark matter flowed along them, draining from the voids, the great empty bubbles of the cosmos, and streaming into the filaments. These filaments are not static lines. They are rivers of mass, dark matter particles, moving under the influence of the collective gravity of the web, drift along these cosmic highways, winding their way toward the nodes, the dense intersections where the filaments cross. It is here, at the nodes, that the massive galaxy clusters are born, the chaotic, bustling metropolises of the universe, built upon the foundations of the deepest dark matter wells. The behavior of dark matter in these filaments is governed by its cold nature, because the particles move slowly relative to the speed of light. They are easily captured by gravity, allowing them to form fine, detailed structures. If dark matter were hot, composed of fast-moving particles like neutrinos, it would stream out of these wells, washing away the fine details, smoothing out the universe into a featureless sludge. But because it is cold, it clumps. It forms a hierarchy of halos, large halos containing smaller subhalos, nesting like Russian dolls. This is why we see galaxies of all sizes, from the giant ellipticals at the centers of clusters to the tiny, faint dwarf galaxies that orbit them. These dwarf galaxies are the visible tracers of the smaller dark matter subhalos, surviving remnants of the early universe that have not yet been cannibalized by their larger neighbors. The computer simulations that model this process, vast numerical experiments running on supercomputers for months at a time, visualize this evolution in breathtaking detail. In these simulations, the universe begins as a smooth purple mist, which slowly curds and fragments, sharpening into a complex network of bright knots and long, thin tendrils, a structure that looks remarkably like the neural network of a brain or the mycelium of a fungus. This is the skeleton of the cosmos, revealed in silicon, showing us that the visible galaxies are merely the bioluminescent bacteria living on the strands of a much larger, darker organism. As the dark matter flows into these filaments and clusters, it drags the ordinary matter with it. The hydrogen gas, floating in the intergalactic medium, feels the gravitational pull of the dark matter threads and falls in. But unlike dark matter, which can pass through itself without friction, the gas collides. It shocks and heats up as it falls into the gravitational wells, converting its potential energy into heat and light. This is why the filaments of the cosmic web are often traced by hot, ionized gas, glowing in X-rays, a warm, hot intergalactic medium that outlines the dark matter spine. When this gas falls deep enough into the center of a dark matter halo, it cools, condenses, and fragments to form stars. Thus, the galaxy is born, a jewel of light cradled in a vast, rotating sphere of darkness. The dark matter halo extends far beyond the visible edge of the galaxy, 10 times larger and 10 times more massive, a protective cocoon that prevents the galaxy from flying apart. Without this halo, the delicate spiral arms of galaxies, like the Milky Way, would never survive. They are transient patterns, stabilized by the unseen mass, fleeting dreams held together by an invisible thinker. There is perhaps no greater demonstration of this separation between the visible and the invisible, no more dramatic proof of dark matter's independent existence than the catastrophic collision of galaxy clusters. When two of these massive nodes of the cosmic web are drawn together by their mutual gravity, they do not merge gently. They crash with the energy of a billion supernovae. The most famous of these events is the bullet cluster 1E0657-56. Here, we witness the aftermath of a high-speed impact between two enormous clusters of galaxies. The collision was a sorting machine, a cosmic sieve that separated the components of the universe based on their nature. The stars within the galaxies, being incredibly sparse relative to the space between them, passed right through each other like two swarms of bees, largely unaffected by the collision. The hot gas, however, which makes up the majority of the normal matter in a cluster, slammed together. It created a shock wave, a drag force that slowed the gas down, causing it to lag behind. Stuck in the center of the collision zone, glowing furiously in X-rays due to the intense heating. But the dark matter, the ghost, behaved differently because dark matter does not interact with light and interacts only weakly, if at all, with itself. It experienced no friction. It did not splash. It did not shock. It simply passed through the other dark matter halo, ghost through ghost, continuing on its trajectory with the stars. When astronomers looked at the bullet cluster, they saw the visible evidence of this separation. They used gravitational lensing to map the mass, to find where the gravity was coming from. If there were no dark matter, the gravity should be centered where the gas is, for the gas contains far more mass than the stars. But the lensing maps revealed that the gravity was not with the gas. It was with the stars, in two massive clumps on either side of the gas cloud. The mass had moved on, leaving the normal matter behind. The dark matter had drifted through the violence of the crash, indifferent to the friction that halted the gas. This observation provided the most direct empirical proof of dark matter's existence, shattering alternative theories that tried to explain the universe by merely tweaking the laws of gravity. Here was matter that we could not see, separating itself from the matter we could see, proving that the universe is composed of two distinct fluids, one that glows and churns and interacts, and one that drifts in silence, dominating the gravitational landscape. This drift is not merely a thing of the past. It is happening now, in the slow, inexorable flow of the local universe. Our own Milky Way is falling. We are falling towards the Andromeda Galaxy, destined to collide and merge in 4 billion years. A dance choreographed by the dark matter halos that envelop us both. But on a larger scale, our entire local group of galaxies is drifting at over 600 kilometers per second towards a region of space known as the Great Attractor, a massive concentration of mass hidden behind the dust of our own galactic plane. And beyond that, the Great Attractor itself is being pulled towards an even larger structure, the Shapley supercluster, a monster node in the cosmic web containing tens of thousands of galaxies. We are caught in a great river of dark matter, a flow known as the dark flow, sliding along the filaments towards the densest regions of the universe. This motion is smooth, continuous, and unrelenting. It is the breathing of the cosmos, the rearrangement of matter on scales so vast that a human lifetime is less than a flickering nanosecond in comparison. Yet within this grand drift, there are subtleties, fine-grained details that challenge our understanding. As we zoom in from the scale of superclusters to the scale of individual galaxies, the interplay between dark matter and ordinary matter becomes more complex. In the centers of galaxies, the density of ordinary matter, stars, and gas can become so high that it begins to dominate the local gravity, altering the distribution of the dark matter itself. This baryonic feedback is a subject of intense study when massive stars explode as supernova, or when supermassive black holes at galactic centers erupt with jets of energy. They can blow gas out of the galaxy entirely. This sudden removal of mass changes the gravitational potential, causing the dark matter halo to expand, to puff up. It is a dynamic feedback loop. The dark matter concentrates the gas to form stars, and the death of those stars pushes back against the dark matter, reshaping the very cradle that born them. This breathing of the halo, this response of the dark sector to the violent astrophysics of the visible sector, suggests a relationship that is more symbiotic than previously thought. The ghost guides the machine, but the machine can, in turn, shift the ghost. The texture of the cosmic web is also defined by what is absent, the voids, those vast, spherical regions of emptiness that occupy most of the volume of the universe, are not truly empty. They are underdense regions, containing perhaps only 10% of the average density of the universe, but they are the laboratories of the isolated. In these lonely expanses, far from the bustling filaments and clusters, small ripples of dark matter can still collapse to form isolated dwarf galaxies, hermits of the cosmos. These void galaxies are pristine, untouched by the interactions and mergers that shape galaxies in the crowded clusters. They drift in solitude, evolving slowly, their dark matter halos distinct and undisturbed. Studying these lonely outposts allows astronomers to test their models of dark matter in a clean environment, away from the chaotic astrophysics of the dense web. And even in the deepest voids, the faint structure of the web persists. Tenuous, wispy filaments of dark matter crisscross the emptiness, too thin to trap much gas, too weak to form many stars, but they're nonetheless a subtle geometry in the nothingness. As we ponder this invisible lattice, we must also consider the role of time. The web we see today is not the web that will exist tomorrow. The universe is caught in a battle between two titans. The attractive pull of dark matter, which seeks to build structure, to pull everything into a single, massive knot, and the repulsive push of dark energy, which seeks to tear the web apart, to stretch the voids until the filaments snap, and the clusters are isolated islands in an expanding sea of dark. For the first half of the universe's life, dark matter was winning. The web grew, the clusters formed, the structure sharpened. But about 5 billion years ago, the balance shifted. Dark energy began to dominate. The expansion of the universe accelerated. Today, we are living in a time when the growth of the cosmic web is slowing down. The Great Drift is fighting against the stretching of space itself. Distant clusters are being carried away from us faster than light can bridge the gap. The filaments are being stretched thin. In the far, far future, the cosmic web may dissolve, the glorious tapestry unraveling as the universe expands into a cold, dark isolation. But for now, the web holds. The dark matter continues its slow work, binding the galaxy clusters, holding the spiral arms of the Milky Way, and guiding the light of distant quasars through the gravitational lenses of the deep. We construct our understanding of this dark architecture through a combination of observation and simulation, effectively reverse engineering the universe by measuring the distortion of light from millions of distant galaxies, a technique called weak gravitational lensing. Astronomers are creating three-dimensional maps of the dark matter distribution. Projects like the Dark Energy Survey and the Euclid mission are scanning vast swaths of the sky, measuring the shapes of galaxies with exquisite precision. They look for the tiniest alignments, the subtle tendency of galaxies to align with the invisible shear of the foreground dark matter. These statistical signals, averaged over millions of objects, reveal the clumping and the drifting of the dark sector. The maps they produce are not of light, but of density. They show us the mountains of mass rising from the plains of the voids. They confirm that the visible galaxies truly are tracing the dark matter skeleton. But they also reveal the subtle offsets, the complexities where the gas and the dark matter do not perfectly align. Hints of the complex hydrodynamic physics at play in the Grand Drift. To visualize the scale of a dark matter filament, imagine a bridge of matter connecting two galaxy clusters separated by 50 million light years. This bridge is not a solid object, but a stream. If you were to float inside it, you would see galaxies drifting past you, carried along the current of the dark matter river. You would see gas clouds, tenuous and hot, stretching along the axis of the filament, and all around you, the invisible particles of dark matter would be swarming, passing through you, through the galaxies, through everything, bound only by the grand gravitational potential of the filament itself. It is a structure of tenuous majesty, a river of ghosts spanning the abyss, and it is the dominant feature of our universe. The stars, the planets, the life forms, we are all just flotsam caught in the eddies of this great, dark flow.